In this slide, I will be presenting Green's theorem, which is one of the fundamental theorems in vector calculus. Green's theorem establishes a relationship between a line integral around a simple closed curve and a double integral over the region enclosed by that curve. By transforming a line integral into a double integral, it simplifies many complex and time-consuming calculations, making them easier to solve. Because of this, Green's theorem has many practical applications in mathematics, engineering, and physics, especially in areas such as fluid dynamics, electromagnetism, and circulation analysis. The theorem was first introduced by George Green in 1828 through his work on electricity and magnetism. Although his work received a little recognition during his lifetime, it was later rediscovered by William Thomson in 1845. Around the same time, Augustin Louis Cauchy independently proved the same mathematical relationship. Today, Green's theorem is recognized as one of the most important and widely used theorems in vector calculus. The main objective of this report is to solve two different equations using Green's theorem. For each problem, we will first perform the solution manually, showing the complete mathematical steps to ensure a clear understanding of the applications of Green's theorem. After obtaining the manual solution, we will use Mapper software to solve the same problem and verify our answer.
I'll be covering the theorem behind our topic, Green's theorem. Put simply, Green's theorem relates a line integral around a positive-oriented, simply closed curve to a double integral over the plane region D that C encloses. In other words, it let us convert a calculating along the boundary of region into a calculation over the interior of that region, and vice versa. Formally, the theorem states let C be a positive-oriented counterclockwise, pieces-wise smooth, simple closed curve in the plane, and let D be the region bounded by C. If P of x, y, and Q of x, y are function of continuous first-order partial derivative on an open region containing D, then the closed line integral of P dx plus Q dy around C is equal to the double integral of D of the partial derivative of Q with respect to x minus the partial derivative of P with respect of y dA. This formula is the foundation for everything we will be calculating in the next few slides. Before I can apply Green's theorem to a problem, there are 5 conditions that must be satisfied. First, the curve must be closed, meaning it starts and ends at the same point. Second, it must be simple, so it doesn't cross itself anywhere. Third, it needs to be a piecewise smooth, made up of infinitely many smooth segments joined together without sharp breaks. Fourth, the curve must have positive orientation, that is, traverse counterclockwise, so that the region D always stay on the left-hand side as we move along C. And fifth, the function P and Q must have continuous partial derivative throughout an open region containing D, not just on D itself. As shown in the diagram here, our curve C is a simple closed curve traced counterclockwise with the arrow indicating direction and region D enclosed inside. Since all 5 conditions are satisfied, we can confidently apply Green theorems to our case study.
Okay, next, for condition not applicable for Green's theorem. Green's theorem is not applicable under the 4 following conditions. If the curve is open, it cannot enclose a region, making the double integral impossible. The second one is, if there are discontinuous partial derivative, any mathematical whole or division by 0 invalidate the standard formula. The third one, if the boundary is not piecewise smooth and excessively judged or oscillating path prevent the line integral from being calculated. And the last one, if the path has a negative orientation, traversing it will yield the wrong mathematical sign. Okay, first one, we start with question 1. Use Green's theorem to evaluate the line integral of over the closed curve C of the vector field f dot dr, where the vector field f of x and y is equal to the quantity sine of x minus x square y in the I direction plus the quantity xy square plus cos of y in the j direction, and see if the boundary of the region bounded by the circle of radius 2 and 3, center at the origin and lying in the first quadrant. Okay, for the manual calculation, to evaluate the integral using Green's theorem, we need find the partial derivative of our vector component first, which we get the q sub x equal to y square and p sub y equal to minus x square. Subtracting p sub y from q sub x simplify the integral to y square plus x square, which is equivalent to r square in polar coordinate. Because the region is counter ring lying in the first quadrant between circle of radius 2 and 3, we set our polar integration bound for the radius r from 2 to 3 and for the angle theta from 0 to pi over 2. Multiplying the integral by the polar area element r gives us r cubed, which integrate with respect to r power of 4 over 4. Evaluating for this 2 to 3 gives 3 power of 4 over 4 minus 2 power of 4 over 4, simplifying to 65 over 4. Finally, integrating this constant with respect to the theta from 0 to pi over 2, yield a final answer of 65 pi over 8.
Now, let's move on to the Maple solution of question 1. To visualize the region, we use Maple's unequal common from the plot's package. We define the quarter analysis using the conditions x greater and equal to 0, y greater and equal to 0, with the radius square bounded between 4 and 9. This corresponds to a quarter of an annulus with inner radius 2 and outer radius 3 lying in the first quadrant. The output confirms that our region matches to the one that we set up in the manual solution. Next, we compute our Green's theorem directly in Maple. We define P as sin x minus x squared y and Q as xy squared plus cos y, matching our manual setup. Taking the partial derivative of P with respect to y gives negative x squared, and the partial derivative of Q with respect to x gives y squared. Subtracting this, qx minus py simplifies to x squared plus y squared. Since we're working in a polar region, we substitute x equals to r cos theta and y equal to r sin theta, which simplifies our expression to just r squared. Finally, we integrate r squares times r over r from 2 to 3 and theta from 0 to pi over 2. Maple returns the result as 65 pi over 8, which matches exactly with our manual calculation.
Now let's move on to our second case study question. Here we are asked to use Green's theorem to evaluate the closed line integral of y to the fourth power minus y to y dx minus 6x minus 4xy cubed dy over the rectangle with vertices of 0, 0, 6, 0, 6, 4, and 0, 4 oriented counterclockwise. As shown on the graph, this rectangle spans from x equals 0 to x equals 6 and y equals to 0 to y equals to 4, with the boundary C traced counterclockwise around the shaded region D. This satisfies all the conditions of Green's theorem we just discussed, so we can proceed to solve it. Okay, let's now walk through the manual calculation. Phi will identify P and Q from the integral. Here P equal to the y to fourth power minus 2y and Q equal to negative 6x minus 4y cubed, which simplified to negative 6x plus 4yx. Okay, now we take the partial derivative needed for Green's theorem. The partial derivative of P with respect to y is 4y cubed minus 2, and the partial derivative of Q with respect to x is negative 6 plus y cubed. Okay, substituting into Green's theorem, we get the double integral of qx minus py dA, which become the negative 6 plus 4y cubed minus 4y cubed minus 2. The 4y cubed terms cancel out, leaving us with the constant negative 4. Since the integrand is just a constant, the double integral becomes straightforward. Now we need to integrate with respect to y from 0 to 4, then with respect to x from 0 to 6. Integrating negative 4 with respect to y from 0 to 4 gives us negative 16. Then integrate negative 16 with respect to x from 0 to 6 gives us negative 16 times 6, which equal to negative 60 and negative 96. So the value of our line integral evaluated using Green's theorem is negative 96.
In this part, we use Maple software to define and visualize the region of integration. First, we load the required packages, which are vector calculus and plots. Then we define the vertices of a rectangle using coordinate points. After that, we use the polygon plot command to plot the region with a light pink color and set the viewing window for better visualization. From the output, we can clearly see the rectangular region on the coordinate plane, which represents the boundary used in our Green's theorem calculation. This helps us visually confirm the region over which the double integral will be evaluated. In this slide, we apply Green's theorem using Maple to verify our manual calculation. We first define the functions p and q, and then compute their partial derivatives, where we find py and qx. Next, we calculate the expression qx minus py, which is required in Green's theorem. After substituting into the double integral over the given region, Maple evaluates the integral automatically. From the output, the final result obtained is negative 96. This confirms the correctness of our manual solution and shows that both methods give the same answer. Using Maple not only helps to verify our work, but also reduces the chance of computational errors in complex integrals.
To conclude, Green's theorem was applied to two problems, a quarter analysis region and a square region. Both were solved manually and then verified using Maple, and in both cases the results match. This confirms that Green's theorem was applied correctly and shows that Maple is a reliable tool for checking manual calculations. Overall, this assignment strengthened our understanding of how line integrals can be converted into double integrals using Green's theorem.